All right, so remember that revised exams are due tomorrow night, right, by 11:59 p.m. So in the meantime, we started to talk more about carbonyl chemistry. And like I mentioned, this is the first of, well, second really, of a number of chapters, and you might start to get the feeling that the number of reactions that we talk about, that we cover, is just going to kind of explode. All right, so if you think back when you were first learning of some substitution reactions, or maybe even elimination, you were thinking, oh, this is so many reactions. It'll feel kind of like kind of quaint now as we get into more carbonyl reactions. So the important thing here to do, I think, is to help organize this, to keep track of two main things. And we talked about them some yesterday. One has to do with the type of carbonyl group, whether it's this type 1 that has a leaving group attached, or type 2 that does not have a leaving group attached. Okay? In addition to that, but together, is the relative order of reactivity. Okay? Because very reactive groups will react with less reactive nucleophiles. If it's down on the unreactive side, then we need a very strong nucleophile to cause a reaction to go. What was the other thing? Those two things, kind of. And as you go through, it's good to keep these reactions organized, two different ways. I think that it makes sense to organize reactions like this is that you can start with a functional group, make some kind of a diagram. Let's say we are going to start with what? An alcohol or something. That's terrible. And your diagram could be asking the question, what can we turn this alcohol into? Right? So we can oxidize alcohols. Right? So we can oxidize that to an aldehyde. We could oxidize it to a carboxylic acid. Right? We remember back, we could do dehydration reactions, right? We could convert that into a halide. We could remove do an acid-base reaction and then do a substitution reaction. All right, so you can start with a functional group and just ask yourself, what can we turn this into? And make some kind of diagram like this. The other important way to apply all these reactions to synthesis is to reverse this, right? Because a lot of times we analyze synthesis in kind of a backwards or retrosynthetic direction. And so you could maybe say, oh, what can I make this aldehyde from? Okay, so we know that we can make it from an alcohol, an oxidation reaction. We could make it from an alkene by an ozonolysis reaction. We could make it from, what else? We could move this one further away. We can make it from an alkyne, right, by hydroboration oxidation. So this ties in a lot of old reactions as well. Okay, but if you kind of organize these, make a diagram for each functional group or something like that, it helps you think about how all of these functional groups are related. Because usually syntheses kind of have two different parts. One part, which we usually do first, has to do with building up a carbon chain, or the ring, or whatever carbon framework. And then the second part of it has to do with functional group transformations, and that's what all of these are. And then you can just say, for example, just for fun, right? Start with this alcohol and just see what you can turn it into, right? You can say, I can oxidize this aldehyde. What can I turn that aldehyde into? Turn it into, we'll learn some reactions today or next time. And just keep converting everything into something else, right? Kind of get a lay of the whole synthetic landscape. And that will help as we do synthesis of all these reactions, and help you remember all the reactions as well. All right, so what we're going to do today, let's look at just what we kind of finished off here. We looked at the different functional groups. We looked at the two general reactions, so the acyl, nucleophilic acyl addition reactions. Right. If there's no leaving group, or substitution reactions if there is a leaving group. We looked at their relative reactivities, we made a table of those. And then we introduced some strong nucleophiles, so basically hydride and then some strong carbonucleophiles. All right, so now we're going to start to react these nucleophiles with the carbonyl groups. Okay, the first one we're going to look at are the hydride reagents, so reacting carbonyls with hydride. All right? Okay. I did bring a clip of that and set it up, so we'll skip it. We can do it tomorrow. All right, so here's kind of where we're at. This is what we've done already, and so now what we're going to do is we are going to learn reactions first of aldehydes and ketones with strong nucleophiles. So hydride is our first strong nucleophile. And then we're going to look at the same reactions with hydride for acid halides, esters, amides, and carboxylic acids. All right. So here's our first reaction. Remember that if we have, this is a sodium borohydride, essentially what it's going to react as is the boron with 4 hydrogens around it like this, and a minus charge. All right, so this is the hydride delivery reagent. So the first thing that happens here is hydride acts as a nucleophile. Hydride has a minus charge, gets it drawn to the delta plus end of the carbonyl. Just like we saw in the generic reactions, though, because that carbonyl carbon can't hold any more electrons, it has to give up some electrons, and it gives them up to the oxygen. All right, we're going to draw out the whole mechanism for this one. So we are going to get an intermediate. What did we call that intermediate? Had that real imaginative name, the tetrahedral intermediate. Why do you think we call it that? Because it's tetrahedral, right? Okay, so we've added an H. We started with an aldehyde. We get to here. There's no leaving group. So then we do step 2. We add water. And all that happens when we add water is that we just quench the reaction. We protonate everything that's basic at all. Okay, including this alkoxide. And we get this product here. All right, so we start with an aldehyde. We get a primary alcohol. All right, so this is a nucleophilic addition reaction, but it's also a reduction. So remember, the way that we term reduction in organic chemistry is either the addition of hydrogen or the removal of oxygen or electronegative atoms. Okay, so if we look at the difference between the reactant and the product, we see that we have added 2 hydrogens, right? The same as just a hydrogenation reaction. So we've added the 2 hydrogens, but not as H2 gas, but we added 1 hydrogen as a hydride, the other hydrogen as a proton. All right? All right, so we can do the same thing with lithium aluminum hydride. Okay, so the reaction works just the same. We started with an aldehyde, so again, we get a primary alcohol. If we do the reaction with ketone, what are we going to get then? It's going to attack here. It's going to go like this. We get this intermediate, right? There's no leaving group. So we quench the reaction with water. And we get a secondary alcohol. Okay? Aldehydes go to primary alcohols, ketones go to secondary alcohols. Okay? This would also work with lithium aluminum hydride. Okay? Same reaction. Now we can also, it's not a hydride reaction, but we can do the same thing using just a hydrogenation reaction. All right, so we hydrogenated carbon-carbon double bonds, and in fact, carbon-carbon double bonds are more reactive than ketones or aldehydes. Okay, but we can still do this. All right, so we just add 2 H's, one on each side of the double bond. And again, well, here, let's put the R group back on there. R. If R is an H, we have a primary alcohol. If R is a carbon or an aryl group, a benzene ring, then we get a secondary alcohol. Okay? Let's just write that we should be more specific here. Ketones and aldehydes are harder to hydrogenate than are alkenes. All right, so that gives us some selectivity. So for example, if we start with a molecule like that down at the bottom, we could hydrogenate this. And if we only use one equivalent of hydrogen, then we can hydrogenate the alkene and not the ketone. Okay? So this would give us the ketone like this. All right, if we put in an excess of hydrogen and we wait long enough, I guess, for the reaction, we can hydrogenate both of those pi bonds. Okay, so H2 excess palladium on carbon. We just get the alcohol, the secondary alcohol, double bonds hydrogenated as well. All right, if we reduce this system with sodium borohydride, we usually do these in an alcohol like methanol, then only the ketone will be reduced and not the double bond. So this gives us some control and some selectivity over the reactions. Okay? All right. Let's see. What am I here? So I forgot to put in one slide, so I'm going to have to add one in here. I know this always messes you guys up. Hydrogenation, or not, the reduction of acid chlorides and esters. Okay, so now we're going into the type 2. We started out with type 1 carbonyls, and now we're going to talk about type 2. All right, so if we start with an acid chloride, if we reduce this, let's say with lithium aluminum hydride, and then water, let's look at what happens. Okay, so here's our hydride reducing agent. So just like before, hydride attacks the carbonyl carbon, form a tetrahedral intermediate. So let's draw out the intermediate here, and we can draw this out. Here's our new H. Of course, we would have a racemic mixture of these two, of the tetrahedral intermediate. All right, so do we have a good leaving group on this one? Yeah, the chlorine or the chloride is a good leaving group. So these electrons are going to come back down to reform the carbonyl, and we're going to lose the chloride. So what kind of a functional group is this going to give us? An aldehyde. And what happens to an aldehyde in the presence of lithium aluminum hydride? It gets reduced, right? We just did that one on a couple of slides ago. All right? So we could draw this out again. We have another equivalent of lithium aluminum hydride. And in fact, they don't go into this, but lithium aluminum hydride has 4 hydrides on it. And actually, it can deliver 4 hydrides, each one of those. Okay, so again, this can then go here, goes like this. We get a new tetrahedral intermediate. This, do we have a leaving group on it now? No. So now we add water. Okay, so this addition of water, so what do you think we get if we have excess lithium aluminum hydride and we add water to it? No, just if we go water and lithium aluminum hydride, no organic reagent or reactant in it. No, there's no carbons. Not hydronium. Hydrogen gas, right? Because we've got H minus acting as a base then, pulling off a proton off of water. Bubbles off hydrogen gas. All right? Heats up too. What do you think happens if you do this too fast? It can explode. All right? Bubbling, it can froth out, it can explode up out of the top of your flask like a volcano. And if it generates too much heat, the hydrogen gas can catch on fire. Okay? So you have to do this very carefully. Lithium aluminum hydride is a very reactive compound. In fact, when I first learned how to use it when I was in grad school and I was being taught by a postdoc in our group, he said that I should actually, when I weigh it out, I should use like a gray powder. And I should use a plastic spatula to weigh it out and do it quickly, because he said if you use a metal spatula, you can cause it to spark. And you don't want it to spark. So you have to be very careful with this stuff. So, in the last step, you slowly add water. You cool it as you're doing that so you can control how fast the hydrogen is being given off. Yeah?
How cold is it?
You probably just in a water bath. I mean, like an ice bath. And in fact, usually we don't just quench with water. There's other ways to do it. Because what happens is you get aluminum, you have lithium, and you get these hydroxides, and it makes kind of like this gelatinous colloidal material that's really hard to filter out. So there's other procedures so you can get the lithium and aluminum salts to precipitate like a crystal material, and so then you can more easily filter them out. Another way to do it is to add something like ethyl acetate, which is just it's an ester, but it's just a solvent. You drip that in, it reduces the ethyl acetate. We'll look at that reaction next. Okay, and that's a way to destroy the excess lithium aluminum hydride. Okay, so if we started with that acid chloride, then it goes all the way to the primary alcohol. Okay? You can't stop it at the aldehyde. So it reduces once, and then it reduces again. There is another specialized reagent. I think I'm going to not crowd this so much, so we're going to have to add another slide too. And this structure is like this, lithium, and where should I put this first? I'm going to put the H there, aluminum, and then it has 3 tert butoxy groups. So it has 3 kind of like ethers around it. And so the oxygens donate electron density to the aluminum, reducing the polarity of the hydride aluminum bond. And so this makes it less reactive. Okay, so we have to do that first. We still have to quench with water. Okay, this is less reactive than lithium aluminum hydride. And so for this reagent with an acid chloride, we can stop the reduction at the aldehyde. Okay, the mechanism would look the same. Okay, stops at the aldehyde. All right. So the next one I'm going to have to do another. So esters are a really common functional group. And we have 2 ways to do them as well. Okay, so we'll just do the simple ester here. All right, if we start with this methyl ester and we reduce it with lithium aluminum hydride, oops, 4, followed by water. Essentially the same thing happened as what we saw for the acid chloride. Okay, so we can draw this one out too. Minus this hydride goes to the delta plus end of the carbonyl. We form a tetrahedral intermediate. Like this. Okay, now methoxide isn't a great leaving group, but we have a very strong nucleophile, the hydride. And so it's a good enough leaving group in this case. So this goes back down, just like we saw for the chloride, and we lose this methoxy group. And what kind of a functional group do we get? An aldehyde again. And just like last time, what happens to the aldehyde? It goes to a primary alcohol. I'm not going to show those mechanistic steps because we've been through that already. Okay, the other byproduct over here was methoxide. All right, and when we quench the reaction, the methoxide also gets protonated. All right, so from an ester, we essentially get two alcohols. All right, and we can look at the split. It gets split right here. The carbonyl, the carbonyl gets reduced to a single bond. So this part is an alcohol here, and then this methoxy group gives us methanol. Okay, so we get two alcohols from an ester. All right, we can also use another specialized reducing agent. And this, oops, that's not what I wanted to do. This one is really probably used much more. And this one has this structure. Like that. So these are isobutyl groups. So this is called di-isobutyl aluminum hydride. Or we oftentimes use an abbreviation, so we just kind of randomly pick out some letters out of this whole thing, and we'll pick the D, di-isobutyl aluminum hydride. So we usually call this dibal with an H like that. Okay, dibal, its main use is to reduce esters to aldehydes. So it can stop at the reactive aldehyde. Okay, so this stops there. Our other byproduct, though, would be the methanol. Okay? Dibal will also reduce ketones and aldehydes, though, right? If it'll reduce an ester, a ketone or an aldehyde is more reactive, right? So it'll reduce those as well. Okay, so we just keep motoring on through here. Okay, carboxylic acids and amides. All right, carboxylic acids, are some of the least reactive, but lithium aluminum hydride is strong enough to react with it. Okay? The main difference in the mechanism, I don't know that I'll do the whole thing here, is that because lithium aluminum hydride and hydride in general is very basic, what do you think is going to be the first step of this reaction? Right, it's going to be just an acid-base reaction because carboxylic acid is acidic. Okay, so the first step is going to be just removal of this proton. And so we get this, and this, in fact, combines with aluminum trihydride, AlH3, just in a Lewis acid, Lewis base. And it actually ends up making the OH into a better leaving group. Like this. Okay, and then from here, it's kind of the same thing that we've been seeing. Another equivalent of lithium aluminum hydride can now come in and react like this. Right, and now we're going to kind of just follow the same mechanism that we've been doing. So we're going to go to a tetrahedral intermediate. H3 minus there, and an H. And then the H with the aluminum on it acts as a leaving group. So this is going to, like these other cases, are going to give us an intermediate that's an aldehyde, which of course then gets reduced again. Okay, so carboxylic acids as well get reduced to primary alcohols. All right, so lithium aluminum hydride just kind of reduces the crap out of everything that you put it in contact with. Okay, now amides are slightly different. Okay, so in all of the other cases, what we've always seen is that we end up cleaving the bond next to the carbonyl and then reducing the carbonyl to the alcohol. Okay, we get something different for amides. And so what happens is we end up losing a water molecule, which includes the oxygen of the carbonyl, and we get an amine. Okay, so this would be called a secondary amide because the nitrogen has 2 carbons attached. Right? And so we end up with a secondary amide. No, a secondary amine. What if we had this amide in a ring like this? This is called a lactam. It's a cyclic amide. So what would we get out of that? Okay, all we're going to really do is remove this oxygen. Okay, so we're still going to have a ring like this. All right, so let's look at how this one goes and why we don't cleave the nitrogen-carbon bond and we just lose this water molecule. All right, so it's going to start out just like with the carboxylic acid, because that NH is somewhat acidic. Okay, so this hydride is going to remove this proton, generate hydrogen gas, and we're going to push these electrons. It's just a different resonance structure, but we're going to push them up onto the oxygen. We have a double bond to the nitrogen, like this. Okay, we have an O minus, like when we had that carboxylate anion, and so this is going to react with the aluminum that has 3 hydrogens on it. Right, this is a neutral one. And so this is just a Lewis acid, Lewis base step. Okay, which piece of this is the Lewis acid? The aluminum, right? It's the electron pair acceptor. We get to here. We have the double bond to the nitrogen. Okay, and so this carbon-nitrogen double bond has a lot of the same properties and reactivities of a carbon-oxygen double bond, right? It's still going to be delta minus on the nitrogen and delta plus on the carbon. All right, so when another equivalent of lithium aluminum hydride reacts with this, the hydrogen is going to go to this delta plus carbon, and the electrons are going to go up onto the nitrogen. Right? These are some of the longest mechanisms you've seen, right? It's pretty fun. Okay, what does that give us? Here's our new hydrogen. A single bond to the nitrogen. We had 1 pair of electrons on the nitrogen already. We have another pair now. And so what kind of a charge, what other charge are we going to have here? We already have one on the aluminum. A minus on the nitrogen, right? So this is going to be a minus charge on the nitrogen. Okay, so it's kind of just, this is a tetrahedral intermediate, right? And the nitrogen with a minus charge is just like we saw before with the oxygen with a minus charge. And so these electrons can come down here, and we can lose this leaving group. The aluminum pulls the oxygen off, and we get to another compound that has another carbon-nitrogen double bond. Okay, this type of compound is called an imine. In the next chapter, we're going to see how to make those. But you'll have to wait until then. All right, so now we're just going to reduce this carbon-nitrogen double bond just like we did this other carbon-nitrogen double bond.
Professor,
Yeah.
did we add a carbon on there, or is that just supposed to be a hydrogen?
Oh, that's supposed to be hydrogen. Yep, thanks. All right, so let's just do the whole same thing again. Right, so we need a lot of lithium aluminum hydride for this, right? Okay, so this is again going to come into this delta plus carbon. These electrons go up onto the nitrogen. We have an H. That's an H. It's a methyl. We're back to the point where we have a minus charge on the nitrogen. So do we have a leaving group on the tetrahedral intermediate now? No, right? Because the tetrahedral intermediate, the carbon that's tetrahedral that we're talking about is that one right there. We have two hydrogens, we have an ethyl group, and then the nitrogen, right? And so what do we have to do now to get to the product? Just protonate it, right? So now is when we bring in the water. Right? So we essentially have to wait for the reaction to finish before we add the water. Right? Because if we add the water too soon, the water is just going to react with the lithium aluminum hydride and nothing else is going to take place. All right, so we get over to here, and we now just have the amine. Questions? Yeah.
So how do we know when at the end when we don't have any leaving groups, or?
Yeah, I think when there's no more leaving groups. Okay, well, and because I told you before that what happened. So in this, if we look at what has to happen, we have to lose that oxygen, right? And so what we're doing, first we're making that oxygen into a better leaving group by coordinating it to the aluminum, all right? And then we just have this carbon-nitrogen double bond, which has to be reduced. All right, so let's...
Theoretically go straight from the one to the left to the amine. How do you pronounce that?
Let's see.
The bond between the oxygen and the carbon. That simultaneously be broken while the hydrogen.
So you mean from here, straight up to there?
Yeah.
Or, well, I think it's like we talked about yesterday. There was one question yesterday that if we had an acid chloride, could our nucleophile come in and we could just draw it displacing the chloride all in one step without forming the tetrahedral intermediate? Right? And so the answer was that we really can't do, or substitutions don't work on sp2 hybridized carbons. So direct kind of SN2 kinds of substitutions. So this is just like that. We're starting with an sp2 hybridized center. We have to go to a tetrahedral intermediate before we can finish the displacement. Yeah.
Does that intermediate at the bottom right actually exist?
All right, so let's just look at a couple of examples here. All right, in the top one, we have this molecule that has, so what functional group is this? It's an aldehyde, that's right. So that's the shortcut that we use for aldehydes. Okay, so the hydrogen is on the carbon, not on the oxygen. Okay, so we're going to reduce this molecule. It has an ester and an aldehyde. We're going to reduce it with sodium borohydride. Anybody know what's going to happen? Yeah, so the question is reactivity, right? So in this case, we have two carbonyls. Which one is going to be more reactive, the aldehyde or the ester? If you remember that list that we made. Aldehydes are more reactive than esters. All right? And our reducing agent, is that a strong reducing agent or a weak reducing agent? Well, we started out in the beginning with two hydride reducing agents. One was strong and one was weak. Is sodium borohydride the strong one or the weak one? How many people think it was the strong one? How many people think it was the weak one? Yeah, it was the weak hydride reducing agent. So sodium borohydride will reduce the more reactive carbonyl, but not the less reactive one. Okay, so sodium borohydride will reduce the aldehyde, but not the ester. Okay, so it will leave the ester untouched. But it will reduce the aldehyde to the primary alcohol. Yeah?
Does it not reduce the ester because it's not strong enough, or just because we're making the assumption that we only have one equivalent of our...
Okay, yeah, good question. So the question it was, are we saying it only reduces one of these groups because I'm only put one equivalent, or because it just won't reduce esters? Sodium borohydride will just not reduce esters. It's just not reactive enough. Doesn't matter how much you add.
And a follow-up question to that, when we see this type of problem, should we assume one equivalent or excess?
I think, well, these have multiple hydrides. I think if it's a problem where it makes a difference, then I'll specify. Okay? But if we have something like an ester, if the ester is going to reduce, then it doesn't matter if we add one or two, it's always going to reduce all the way. Okay? Because in fact, if we think about the reaction, if we reduce the ester once, we get an aldehyde. And what's more reactive, the aldehyde intermediate or the ester that we started with? It's just like the first problem. Right? The aldehyde is more reactive, so the intermediate aldehyde is going to react first before the ester is. Right? So we just wouldn't get to completion. Right? It wouldn't stop. All right, so what about the next one? The next one is an ester. It's a cyclic ester. Cyclic esters are called lactones. Okay, remember we reduce an ester with lithium aluminum hydride, and what do we get? We get 2 alcohols. All right, so if it's a cyclic one, the carbonyl is going to be reduced to an alcohol like this, and the other oxygen just remains like that. Okay, so we've reduced it, we get our diol. In this case, the 2 alcohols are connected because it was in a ring. All right, we get 30 seconds. We're using dibal. H, what's the special thing about dibal when we use it to reduce an ester? Stops at the aldehyde. So this would give us benzaldehyde plus isopropanol. And if we reduce amides with lithium aluminum hydride, what do we get? Yeah, it kind of chops off the carbonyl oxygen, right, and gives us an amine. Like this. All right, so clearly, even just today, we went through a lot of different reactions, right? So you're going to have to make some lists of these reactions or diagrams and practice them, right? Just reading through the notes on this kind of thing is just not going to be enough, right? Okay, so I will see you guys in the morning then.